One of the questions we might have is, when do we see other types of orders like logarithmic order? A great example of situations where we might see that would be in the case of some while loops. So sometimes these are known as maybe a do while, is what we may have heard of before. And the idea here with the do while loop is basically it's kind of like a for loop, except it doesn't have a termination time, meaning it'll keep on doing the instructions, and in this case here what is happening here, that will continue to happen while this value n is less than, in this case, 1000. So how do we write a time complexity for this? Because it really does depend on the initial value of n. But if n is a quantity that is specified by the user, then n could be really, really small. And so the way we want to approach and think about this is every single time this condition is checked. So our computer arrives here and says, all right, you want me to do this instruction while n is less than 1000. So then it jumps to the instruction and it takes n and it multiplies it by 1.5 and then reassigns it to n. So if n was 10, then after this while loop would iterate, because it would say, okay, n is 10 and that's less than 1000, so let's multiply that by 1.5. So that would give us 15. And now we'd come back up here and we'd say, okay, n is 15, that's still less than 1000, multiply it by 1.5. So essentially what would keep on happening is we would take n, all right, and let's just, worst case is always that the condition is satisfied and that you do have to execute the code. So what's going to happen to n, the initial value of whatever n is coming into this code? Well, it's going to get multiplied by 1.5. And then we come back up to the condition and we say, all right, is n less than 1000? Okay, it is. Well, whatever 1.5 of n is, we're going to take 1.5 of that again, right? Because assuming it's less than 1000, then this is going to get multiplied by 1.5. And that gives us some number, right? We get some number out of that. And then the condition checks again and it says, all right, is n less than 1000? And perhaps it is. And so it gets multiplied by 1.5, right? And it will continue doing this. It will continue doing this until, well, it's going to do it until n reaches or exceeds 1000. So if, let's say, n is 999, and then it gets multiplied by 1.5, and that's approximately right around 1500, and then it checks it again, and it's like, okay, well now n is bigger than 1000, so let's terminate, let's exit out of this loop and move on to the next instruction, should there be one. So basically what we need to ask ourselves is, how many times will n get multiplied by 1.5? And more specifically, how long or how many factors of 1.5 are necessary? And we'll frame it like this. We'll say to reach n equals 1000. Why? Well, because that's the borderline between the loop continuing to run and the loop discontinuing. So basically, in order to answer this question, we have to formulate this as, well, we'll have, let's say, x factors of 1.5 multiplied by n, okay? Because remember, this is just repeated multiplication by 1.5, and the multiplication is associative, so we could multiply all the 1.5s together first, and then multiply the result by n, and we're looking to reach 1000. Okay, greater than or equal to 1000, but since 1000 is the borderline, we'll just set it equal to 1000, and that'll give us the exact value of x that will be necessary. So how do we solve for x now? Well, let's divide by n. So this will give us 1.5 to the power of x equals 1000 over n. And then how do we get a variable down from the exponent? Well, I will write off to the side here a property of logarithms. And this particular property of log says that if you take the log of a to the power of b, that is the same thing as b times the log of a. Okay, so essentially all we have to do here is take the log of both sides, because that will enable us to get that x out of the exponent and down as a coefficient of the 1.5. Remember, we have to do the same thing to both sides. 1.5 to the x is equal to 1,000 over n, so the log of 1.5x must be equal to the log of 1,000 over n, because these two quantities are the same. So the log of one must be the same as the log of the other. Okay, well that gives us x times the log of 1.5 equals the log of 1,000 over n. And now solving for x, that's just a matter of taking log of 1,000 over n divided by log of 1.5. Now this may, be like, well, is this logarithmic order? I thought logarithmic order was just log of the unknown, which in this case we're dealing with n as our unknown. X will just tell us the number of times this is going to run, right? And so this is the number of runs of the while loop. And I'm going to do I'm going to add one or two properties here and of logarithms. The second property that may be useful in seeing that this is just log n, order log n, is this property. It says that the log of a divided by b is the same thing as the log of a, I guess I don't really need the parentheses there, log of a minus the log of b. So I'm going to impose that on this right here. I'm going to use number 2 to split that apart, because what that will give me is x is equal to the log of 1,000 minus the log of n, and that is all over the log of 1.5. It's all over the log of 1.5. So I could take this over the log of 1.5, and I could take this over the log of 1.5. And what I want you to notice here is that here now we do see that we have log of n. And dividing by log of 1.5, that's just a coefficient, that's a constant. So really this expression here is the same thing as negative 1 over log of 1.5, that's just the coefficient of the log of n. So see, this is order log of n. And the log emerged quite naturally because we didn't know how many multiplications by 1.5 would be required in order to exceed a value of 1,000. Now, we're almost done. So we could technically leave it in this form here, that is log n by properties. But remember, this is the number of runs of the while loop. And so each time there will be, let's see, how many flops? Well, there's an assignment and then there's a multiplication. That's 2 flops times, and then that's going to require x total iterations. So we'll have x iterations per flop. So I'm sorry, 2 flops. It says 2 flops per 1 iteration multiplied by x iterations, and that will of course leave us with units of the total flops. So this will be 2 times x, and now just put it in terms of the unknown quantity, right? Because x was something we introduced, representing the number of multiplications that would need to take place. And we just found out that x is equal to log of 1,000 over n divided by log of 1.5. So again, no need to simplify that. I just really wanted you to see that 1,000 over n, it splits up because of property number 2 here. And there we go. So this is the time complexity function for this block of code. And this is exactly where we see logarithmic